final announcements on the board here. So this week in lab, you're going to have your experiment 14 data analysis, data discussion. And we're going to talk about your tables that you need to put together today. Then there'll be, at some point, evaluations during the lab. You'll clean up not only your drawer and make sure your drawer is in really good condition, but you'll have another cleaning up job as well. Make sure that you bring your drawer key with you, or if you've lost your key, bring $10, because that's what it costs to replace the key. So make sure you have your $10 with you. Otherwise, we will come find you to get the $10. So bring the $10 with you. At some point, your experiment 14 report is due. Talk to your lab prof about that. They will give you what the specifics are for that due date. Remember, our final exams, and the other part of lab lecture today, besides the data analysis, is going through the practice exam. So our final exam is next Monday, a week from today, 12:30 to 2:30, right in here. Please wait out in the hallway until you're allowed into the room. We'll actually take this room and the room next to us to get everybody spread out. So don't come early and pick out your seat, because you're probably not going to end up in that seat. So wait out in the hall, and then we'll call you in when we've got all the exams ready to go. And then like I said, I'm going over the practice exam today. I'll post the key on Moodle later this week of what I go over. Okay. So things for the exam. I've got this list over here, so you may want to record these today. Make sure you bring to the exam a calculator. Cell phones can't be used as a calculator, so a calculator. A ruler. TLC, you had to make measurements, so a ruler would be handy. And then pencils and eraser. If you register with Academic Success Center to take your organic lecture exams and are going to be taking your organic lab exam there, you need to get me the paperwork today so that can get signed, because since we have our exam on Monday of exam week, paperwork needs to be taken care of right away. Okay, so see me after lab lecture today with that paperwork. So a couple things before I start going through the data analysis. I'm going to go over, there's 4 tables that you need to put together for experiment 14. They're on page 14.7 and 14.8 in your lab manual. Then after those tables are described, there's a bunch of questions that hopefully you'll be discussing in lab this week. But those are the questions, those are the topics you need to address in discussing these tables in your experiment 14 conclusion. Now what you don't want to do is give question number 3, answer. Question number 4, answer. You want to incorporate your answers in paragraph form into the conclusion that you're writing for experiment 14. And make sure you completely answer the questions. The other thing is, don't forget, now that you have your GC data, you needed to use that GC data to help you figure out what the yield was for your reaction. So make sure you use that GC data not only for putting the tables together, but also figuring out how much alkylated product you have to calculate your percent yield. Okay, so remember that for your report. And then a couple things to think about. So we've got carbocation rearrangement happening, which is a thermodynamic versus kinetic effect. And then we have the substitution, where that occurs on the aromatic ring, a kinetic versus thermodynamic effect. So if it's helpful to differentiate between the two, you can think about the carbocation rearrangement as such, which would occur with the 1 bromopropanes, okay? So either it adds kinetically, it didn't rearrange, or it rearranged and you get the thermodynamic carbocation, okay? And then there is the substitution that is either going to add in kinetic fashion, or you're going to get your alkylation in thermodynamic fashion, okay? So there's 2 different things that you're looking at, and when you're going through the questions for the conclusion, make sure you're paying attention to what it is really asking you, because there's 2 different aspects of kinetic versus thermodynamic that you have to discern between, okay? So be careful with that. So what I have up here on the screen is an example of what your table 1 should look like. So the data that I'm using is conditions A data, and the peak list for that data is up here, okay? The first table, table 1, what you are asked to do is list the compounds that you can identify, list the standard retention times for those compounds that you have standard retention times, the experimental retention time, so the retention time from this column here, under minutes, retention time minutes, and then the experimental percent area, which is going to be this percentage over here, okay? For table 1, it is just your data that you are looking at, all right? So you're going to, and don't use these standards. These are standards that went with this data that was acquired a couple years ago, okay? So use the standards that you were given by your lab prof for analyzing your data. They're going to be similar, but they're not going to be exactly the same. So the first thing is to go through and identify toluene, and then all of the different propyl and isopropyl products. So we've got these guys here, and they're listed on the standards in the order that they should occur. If you have anything between something in the 2.8586 region and then into the 7s, that's probably an unknown, because if it's not one of the isopropyl or propyl toluenes, then you probably can't identify it, okay? So be careful, though, when you're identifying things in between this guy and this guy as unknown. Make sure it's just you're not catching your first meta-isopropyl toluene, okay? Then after the propyl toluenes, things that you can identify are the dialkyl toluenes. They come in the range of 13 to 15 minutes or so. So this isn't on those standard retention times, so you're going to want to write this down. 13 to 15 minutes or so are your dialkyl toluenes. And then your trialkyl toluenes are in the 19 to 21, 22 minutes or so, okay? So every time you add another alkyl group on the toluene, you add 6 to 7 minutes. So that's why we're starting in the 7-ish minutes. Then we go to the 13 to 15 minutes, and then with the trialkyl, we go into the 19 to 20, 21 minutes. So potentially, this guy here at 26 could be tetraalkylated. Maybe yes, maybe no. For this example, I've just labeled it as unknown, because you don't really have to do anything with the tetraalkylated, okay? So this is just your data, is table 1. So when you go for your data discussion, you can't really compare your data to someone else's for table 1, because it is just your data. So make sure, double check your table 1 to do a good job with it, okay? Because there's no double check for you for that one. Okay, the second table, we're going to look at percentages of the components. And so for table 2, we're going to look at these percentages for each of the different reaction conditions. So you want to label your table. First of all, label it table 2. Put a header for compounds, and we'll label our toluene, isopropyl toluenes, propyl toluenes, dialkyl toluenes, trialkyl toluenes. And then across, you're going to have your percentage for experiment A, experiment B, experiment C, experiment D. To come up with these percentages, we're going to have to do some math. So what you're going to have to do is look at the data for each set of conditions, okay? So you got to look at the peaks that you're going to consider for this table, and you've got to come up with a new total peak area, okay? So the peak area and the total peak area is how these percentages were calculated, okay? But you can't use their peak area that you were given on the chromatogram, because now we're looking at a specific portion of those peaks, all right? So you've got to take the peak areas that correspond to each of these different types of peaks. So we've got our toluene, so we're going to count this peak area, and then all the isopropyl toluenes. So we've got to count all these isopropyl toluenes in that what we're adding together. Then we need all the propyl toluenes, so that's this group here. Then we'll get into our alkyl group, so that group here, and then our trialkyl group, that group here. So all of these peak areas for this example, we need to add up and come up with a new total, okay? And that's what you're going to divide by. Then you're going to take each of these pieces and take that peak area divided by that new total. So for toluene, it's easy. We're going to take the peak area of toluene divided by the new total times 100%. That's the percentage we get for the toluene that's left. For the isopropyl toluenes, we're going to have to add these three guys up, divide by that new total that you came up with, times 100%. That's your percentage of the isopropyl toluenes. And so you'll do the same thing for the propyl toluenes, then the dialkyl toluenes, so these guys in here, and then the trialkyl toluenes, so these guys in here. Your check for if you've done this correctly is it should all add up to 100%. If you've added everything up correctly and added the areas correctly and then calculated the percentages correctly, it should add up to 100%. Okay? Questions with the calculation? Yes?
So those calculations don't have the unknowns counted in? That's what you're making?
No, yeah, no unknowns. You only want to count, take into account what you can label as each of these type of compounds. Yes?
So from our total area that's given, to get our new total area, we're subtracting those ones that we're not looking at that we marked as unknowns, right?
Or just add up the ones that you're looking at. So yeah, just be careful in the math that you get the right area. Okay. So you're going to do this for all 4 reaction conditions. So when you guys get in your groups to discuss data, make sure you double check your table 2, because you've got to do it for, have to have the data for all 4 reaction conditions. Double check your data with the other people's data to make sure you've come up with the right numbers. Because now for table 2, your table 2 should agree with the other people that are in your group. Okay? All right. So then table 3, we're going to look at only the isopropyl toluenes. So all we've got to do is add up. Our total area is going to be just these 3 numbers for the isopropyl toluenes, get a new total, and then take each one and divide it by that new total. Okay, so for this table, you're dividing by the sum of these 3, and then you take each one of these divided by that new total. Everyone see that? So it's only 3 things you've got to add together, so it gets a lot smaller than the previous table. And again, you want it for all 4 reaction conditions, and for each experiment, what you come up with should add up to 100%. That is the check, is to make sure it adds up to 100%. Okay? All right, table 4 is then the propyl toluenes. So that's these guys here. You probably will only have something to populate in experiment A and experiment B, right? Because you shouldn't have made a whole lot of propyl toluene in D and C, or C and D. I did, though, in looking at the GC data, there are some that very small amounts, but there are some that showed up in condition Ts, okay? So if you do have some, make sure you do report it, all right? And actually, one thing to mention with the isopropyl toluene, sometimes in condition A, we won't even see our ortho isopropyl toluene. So if that were the case, there was a note on your chromatogram that at that retention time, it was less than 0.5%. It's so small, it wasn't integrated. Okay, so if you've got a note on your chromatogram that's like 8.01, 8.02, less than 0.5%, that means that peak was so small it was less than 0.5%, and probably even smaller than that. Okay. But you'll do the same thing you did for the isopropyl toluenes, add these three numbers together, then divide by each individual number, make sure that everything adds up to 100%. And most likely you'll have A and B populated with maybe something in D, maybe not. All right? Yes?
For our first two tables, should we fill in those standards that we just talked about for the dye and the tri substitute?
Yeah, use the numbers I gave you.
And put them in for the standards?
You can, yeah, you can give the rough numbers.
Right.
I mean, we don't actually run any standards for the dye or tries. That's just the trends you can see in looking at the data. All right. Questions with the tables? Yes?
So those questions are listed after tables. We don't have to have answers for those ready for tomorrow, right? That's what we're discussing in class tomorrow?
Most likely, yes. Yeah. So my lab, yes, which would be specifically DQ. But in general, like, go by what your lab prof told you as far as how the data discussion is going to be handled this week in lab. Okay. So, and some of those questions are not. The questions are not necessarily easy questions. This is a pretty complex data analysis. So that's why you want to make sure you keep track what you're looking at. And the other thing is when you're looking at the data, remember, when you're looking at the isopropyl toluenes and the propyl toluenes in this set of data, that was just a small amount of what actually happened with this data. So depending on the data, you know, some of the conditions, you may be looking at propyl toluenes and isopropyl toluenes and looking at percentages that don't necessarily make sense, but go back to your table 2. That's why you have your table 2 to help remind you, okay, I'm looking at these isopropyl toluenes, they don't make a whole lot of sense, but in the end it was like 2% of the total product. Well, 2% of the total product's not making sense is a little bit better than the whole, 98% of it, okay? So just be careful when you're looking at the tables. Don't forget, especially table 2, where it breaks down the pieces for an entire data set, what all those percentages are. Okay? All right. So remember, you're coming this week, however your lab prof told you, prepared with those tables. Okay? All right, now move this over. We're going to do rapid fire as fast as we can through the exam. And so the exam itself is posted on Moodle. The blank practice exam. Not your exam. Your practice exam is posted on Moodle. And then at the end of this, at some point this week, I'll give you the key, but I kind of want to make sure everybody's had a chance to work through the exam. Okay. So, and if you need extra paper copies, there's still extra paper copies of this on the window ledge outside the stop. All right? Okay, so first page, don't forget, there's a point on the first page. Don't forget to mark your lab section. Okay? Don't lose the easy point of the whole exam. Okay, question number one. Which of the following mixtures cannot be separated using an aqueous organic extraction using hexane and aqueous sodium hydroxide? So here's all our possibilities. What do you need to make that work?
Polar and non-polar.
Beyond that, you need what? What does one of these compounds need to be able to go into? In the water, right? In the aqueous layer, okay? So, does each of these pairs have something that can go into the aqueous layer? Yes? Okay, how about pair A? Yes? B? No. So that is the answer. C does and D does. So the ones that have the carboxylic acid can be deprotonated and go into the aqueous layer, like in experiment 1. Okay? But B could not. Okay, during a recrystallization, If more solvent than necessary is used, how would the recovery be affected? The recovery would be higher because more of the compound would dissolve at high temperature. The recovery would be higher because more impurities would dissolve. The recovery would be lower because more of the compound would remain dissolved after cooling. The recovery would be lower because the impurities would dissolve better. The amount of recrystallization solvent does not affect recovery. So which one is it? C. If you use too much solvent during recrystallization, you're going to keep what you're trying to get to recrystallize and crash out, precipitate out, to stay in solution, and you won't get the recrystallization to work. Which of the following statements about melting points is false? A high melting impurity always broadens and raises the melting point of a pure organic compound. False, okay? If the addition of compound A to compound B does not affect the melting point of B, B must be identical to A. True. If the addition of compound A to compound B alters the melting point of B, B must not be identical to A. True. And melting points determined in the organic laboratory always extend over a temperature range. True. Okay, so the answer, the false one, was A. Okay. The conformation of butane with a dihedral angle of 60 degrees between the two methyl groups viewing down the C2-C3 axis is called gauche, eclipse, anti-stagger. Gauche. So remember the angle when you're looking down an axis that's 60 degrees is gauche. Eclipsed is what? 180, and anti can be similar, and then staggered could be a random, right? As long as they're not overlapping, okay? And actually, sorry, eclipsed isn't 180. Eclipsed is what? 0. Anti is 180. Staggered could be anywhere in there between 60 and 180. Which of the following dimethyl cyclohexanes would you predict to have the least strain in its most stable chair conformation? So to have the least strain of something that is on a cyclohexane, what would be the best way to have that? Axial or equatorial? Equatorial. Okay. So with A's conformation, is that both equatorial? No, you've got one axial, now I'm stuck on anti. One axial and one equatorial. How about B? Yes, you could have, they would either both be axial or both equatorial, right? Okay. C would not, right? C would be axial, one equatorial, and same with D, one axial, one equatorial. So the answer is B. Which of the following results would indicate the presence of an alkene in a bromine test to an unknown? A yellow precipitate forms. B, the solution turns orange. C, the solution remains colorless after addition of several drops of bromine solution. D, the solution gradually goes from orange to colorless after the addition of only a few drops of bromine solution. E, the solution changes color and a brown precipitate forms. So which one would be the positive? C, right? The solution remains colorless after the addition of several drops of bromine solution. Because if you're adding it and it's staying colorless, it is reacting. D, it goes gradually from orange to colorless after only a few drops. Potentially you're not looking at a positive result for an alkene. Maybe something else is going on. Okay, so C is the answer. Which of the following would not improve the separation of two liquids using fractional distillation? So this one's tricky because you guys didn't do experiment 4 this year, which was the fractional distillation. So the answer for that guy is B. If you cooling the fractionating column with water running through the jacket does not improve the separation. Okay, the IR spectrum below contains which of the following functional groups? Ketone, carboxylic acid, alcohol, alkene. Do you see a ketone in there? No. Remember ketones, what range would you see a ketone? 1700s or so. And what are carbonyl stretches? Are they usually weak stretches or strong stretches? Really strong stretches, okay? Carboxylic acid, do you see anything there? No. We probably in this 32, 3300 region see something there. Alcohol, not a nice broad stretch over here again, 32, 3300. Alkenes? Yes. So you've got your stretch here in the 1600s as well as the peak over here in the 3000s. Both of those pointing to an alkene. So the answer is D.
What's the main distinction between carboxylic acid versus alcohol, the OH stretch?
Usually a carboxylic acid is not as nice and broad. There's shifting in it too. It's not like they don't usually overlap. But also a carboxylic acid's not, like an OH stretch is a nice broad stretch. Usually a carboxylic acid's more a tighter stretch. Not as tight as like a carbonyl, but it looks different than an OH. And probably if you had a carboxylic acid, you'd add other information to help you. Okay, so I have to kind of show you the math here to be able to explain this one. Okay, so number 9, we're looking at this Friedel-Crafts reaction here. And we need to calculate the theoretical yield of the cymene. So isopropyl toluene is also known as cymene. So that's where this name is coming from. We have 15 grams of toluene that's reacting with 7.8 grams of 2-bromopropane and 2.4 grams of aluminum chloride catalyst. And we need to figure out the theoretical yield. So first, we need to find our limiting reagent, okay? So the toluene, if you calculate its moles, it's 0.163. So you take your 15 grams divided by the 92 grams of its molecular weight, 0.163 moles. 2-bromopropane, if you divide 7.8 grams by its molecular weight, you come up with 0.0634 moles. And then what about the aluminum chloride? Do we take that one into account? Yes? No? No, because it's the catalyst, right? So it's not going to be a limiting reagent. Okay. So here's our limiting reagent. Multiply 0.0634 moles times our molecular weight. We get 8.5 grams. So the answer is C on the yield calculation. Okay. For number 10, we're looking at the formation of myristic acid. Okay, trimeristin with sodium hydroxide. At reflux, the hydrolysis goes on to form so our myristic acid and our glycerol. The myristic acid formed upon hydrolysis of trimeristin would have which of the following prominent absorbances in the IR spectrum? So myristic acid, what are you going to see there? You're going to see an OH stretch, which is usually somewhere in the 3000s, right? Okay, so probably B or C would be a possibility. What else will you see? You'll see the carbonyl, so where is that going to be? That's going to be in the 1700 region. And then what else will you see? All these sp3 CH stretches, right? In the 2900s. So the only one that lines up with all those needs is B. So 3250, 2950, and 1700. Okay? Whereas here, this 3000 is more like an sp2 CH stretch. We don't really have anything we've talked about for you guys. This is probably around carbon dioxide for 2250. And then 1695, it could be a carbonyl, it could be an alkene maybe. Okay? So B is the best possibility. Which compound is most polar? Something that dissolves in ether but not water, water but not ether, both ether and water. And B, right? If it's only dissolves in water and not ether, it's going to be the most polar compound. And that goes back to solubility tests in experiment 6. Okay. In separate tests, an unknown compound gives an orange precipitate from the 2,4-DNP test, a red-orange solution following treatment with bromine, and an orange flame in the Beilstein flame test. Which of the following compounds is consistent with these results? So the DNP test tells you it's a, if you get an orange precipitate, you've got a ketone or aldehyde, and you guys mainly were using it for ketones. Bromine test, what does that tell you? Negative result, right? So no alkene. And flame test, no halogen, okay? So you want the ketone with no halogen, so that's going to be answer D. And remember, aromatic rings aren't going to react with our bromine and permanganate tests. Trimyristin is a white solid that makes a heterogeneous mixture when added to 2 molar sodium hydroxide. When refluxing 2 molar hydroxide, however, the solution becomes clear. What best explains this observation? Refluxing breaks the trimyristin into C4 and smaller fragments that are water-soluble. Deprotonation of trimyristin gives water-soluble anions. Hydrolysis yields water-soluble anions of myristic acid. Trimyristin is very slow to dissolve. It just takes time. C. So when you do the hydrolysis with trimyristin, you get water-soluble anions of myristic acid, which were your sodium myristate. So answer C. The molecule giving the following IR spectrum would give positive tests for which of the following characterization tests? Ferric ammonium nitrate, silver nitrate, potassium permanganate, or 2,4-DNP. So what do you see in this IR spectrum? What functional group jumps out at you? Yeah. Alcohol, right? The OH there, nice OH. So which test? A, the CAN test, ferric ammonium nitrate. Okay. Why does one determine a percent recovery for the amount of trimyristin obtained from nutmeg, but a percent yield for the amount of myristic acid obtained in the same experiment? The terms can be used interchangeably. Percent yields are only calculated following recrystallization, and the trimyristin was not recrystallized. The myristic acid is a liquid, while the trimyristin is a solid. The exact amount of trimyristin in nutmeg is unknown, so a yield cannot be calculated. Answer D. We know an approximate amount, but we don't know the exact amount out of the sample you were using. Hydrolysis of trimyristin can also be performed by refluxing the compound in an acidic medium such as 1 molar HCl. How would the reaction proceed differently from basic saponification under these conditions? Myristic acid produced would have a much greater molecular weight. The reaction would go faster and only require 15 minutes. At the end of reflux, the product would be soluble in the reaction solvent. The acidic conditions would require specialized glassware. C, right? Because at the end of hydrolysis of trimyristin, you have to protonate it to get the acid. So it's not soluble in base. However, if you've got acidic media, it is going to be soluble. Your final myristic acid would be soluble in the acid. A student forms a Grignard reagent with 1-bromobutane and reacts it with butanal. After acidification and appropriate workup, the major product will be 5-octanol, 4-octanol, 5-octanone, 4-octanone. 4-octanol, right? Because the OH is always off the carbon of the carbonyl of the aldehyde. Remember that from the mechanism, okay? So it's going to be 4-octanol. During the workup of a student's experiment 8 Grignard reaction, following the acid quench, the student forgets to complete a wash with sodium bicarbonate. When distilling the final product, the student obtains a single fraction boiling between 75 and 100 degrees. The final product should have a boiling point of 174 degrees. What is the likely identity of the compound in this fraction? Diethyl ether, the corresponding ketone of the expected product, the corresponding alkenes of the expected product but impure. Thoughts on that one? So you don't do the bicarb wash. what's going to happen? You're going to take your alcohol and basically go on and make alkenes, right? You go ahead and dehydrate it, okay? So the answer is C. Why is it important to carefully exclude water from the Grignard reaction? Water reacts with a magnesium metal to form a flammable hydrogen gas. Water hydrolyzes the aldehyde to form a diol. Water causes the solvent to be too polar, stabilizing the transition state and causing the reaction to be slower. Water rapidly reacts with and consumes the organomagnesium halide. Answer D, right? Okay. Final product from Grignard reaction was isolated by distillation and then characterized. Which experimental observation or method of characterization gave the most useful information about the chemical class of the final product? IR spectroscopy, 2,4-DMP tests, gas chromatography, or solubility tests. And so functional group would be A, IR spectroscopy. Why was sulfuric acid chosen to complete the elimination reaction performed in experiment 11? HSO4 minus is a good electron donor. HSO4 minus is a strong Bronsted base. HSO4 minus is a weak nucleophile. H2SO4 is a weak acid. C. HSO4 minus is a weak nucleophile. So you didn't want there to be a resulting strong nucleophile like Cl minus if you used hydrochloric acid, because then you would end up causing substitution as well. If a GC trace shows several compounds with poor separation and shorter retention times, which of the following changes would not lead to better separation? So a longer column, a column with a stationary phase similar to the compounds being analyzed, a cooler oven temperature, a cooler injector temperature. So what would not help as far as the separation? Where is the separation taking place? So the separation occurs on the column, right? Okay, so a longer column is going to help. A column with stationary phase, more similar to the compounds, will help separate things out. A cooler oven temperature, so you start slower in getting the gradient to get to the separation, will help. But the injector temperature is not going to do anything with the separation. So making it cooler is not going, it would probably hinder it instead of helping it to make it cooler. You want to keep it warm so it goes on as a gas. The alcohol 3-hexanol underwent elimination reaction with sulfuric acid, as was completed in experiment 11. What product do you expect to be formed in the greatest amount? Exclusively 3-hexanone, predominantly trans 2-hexene, predominantly trans 3-hexene, relatively equal amounts of trans 2-hexene and trans 3-hexene. D, right? You should get 2 and 3-hexene, and trans would be more preferred over cis, but not absolutely only trans. In the absence of appropriate standards, gas chromatography is most useful to determine the identity of an unknown compound, determine the purity of an unknown compound, determine the boiling point of an unknown compound, determine the polarity of an unknown compound. So without standards, you're not going to figure out A, right? So B, you will still be able to see how pure it is. You will still get the purity data. You just may not be able to identify the peaks. So it would be answer B. Let's see if I have any voice here at the end. All right, in experiment 7, we converted ethylbenzene to 1-bromoethylbenzene, and it was used to produce styrene. The styrene was then converted to polystyrene. In this sequence, quinoline was used to provide a slow, steady source of radicals for benzoic bromination, provide a slow, steady source of radicals for radical polymerization, provide a slow, steady source of bromine for electrophilic bromination, provide a slow, steady source of bromine for benzoic bromination, act as a non-nucleophilic base to remove HBr from the bromination reaction, act as a non-nucleophilic base to remove HBr from the elimination reaction. So which of that sequence was it involved in? The quinoline was F, part of the elimination reaction, right? So it is used to remove HBr during the elimination reaction. In experiment 7, the reaction of ethylbenzene and N-bromosuccinimide is an example of an elimination, an electrophilic aromatic substitution, a free radical substitution, a free radical addition, a nucleophilic substitution. So before we get to whether it's electrophilic or free radical or what type of reaction is it? It's a substitution reaction, right? And with the NBS, we had a radical, right? So it's going to be a free radical substitution, number C, or letter C. In the free radical polymerization of styrene, if you use 3 grams of AIBN instead of 0.03 grams, so 0.3 grams of AIBN instead of 0.03 grams of AIBN as prescribed in the lab manual, what result would you expect to occur? A full equivalent of AIBN is not necessary because the initiator is only a catalyst in the reaction. It therefore doesn't matter how much AIBN is used, the same length and amount of polymer will result. AIBN is already in excess and styrene is the limiting reagent, so adding more AIBN will not affect the amount or length of polymer formed. The yield of polystyrene isolated by precipitation from methanol will be greater because AIBN is a radical initiator and longer chains of polymer will form, which would increase the amount that is isolated. Or the yield of polystyrene isolated by precipitation from methanol will decrease because AIBN is a radical initiator and more chains of polymer will be formed, but they will be shorter in length and harder to isolate. So answer D, right? So too much AIBN would make short chains of polymer, and with the precipitation that we used in the polymerization, we were only going to get our long chain polymer to precipitate out. If you accidentally used 100% ethyl acetate rather than the assigned 1:1 ethyl acetate hexane mixture as your TLC eluent in experiment 12 and 13, what would you observe on your TLC plate? All the spots would travel further up the plate, all the spots would travel less up the plate, polar spots would travel further up the plate, but non-polar spots would travel less far. Non-polar spots would travel further up the plate, but polar spots would travel less far. Answer A, all the spots are going to travel further up the plate. So if you make the solvent more polar, you're going to increase the RF values of all the spots that you are trying to evaluate. Okay. If you accidentally used 1:1 ethyl acetate hexane mixture instead of 100% ethyl acetate as your Diels-Alder reaction solvent in experiment 12 to 13, what problems are likely? Cyclopentadiene starting material would be less soluble, and phenolmalamiamide starting material would be less soluble. The reaction might be slower as the less polar solvent would not stabilize the ionic transition state of the Diels-Alder reaction, both A and C or both B and C. Thoughts on that one? Answer B. So that N-phenolmalamiamide needed 100% ethyl acetate to dissolve, and if you use the 1:1 hexane ethyl acetate, you wouldn't get it to dissolve before you added the cyclopentadiene. So that would be the problem with that one. Okay, I've got to kind of cover the answer on this one and show you all the answers. Which mixture of Diels-Alder adducts might be expected when 2-methylfuran and Z-beta cyanoacrylic acid are combined? So 3 and 7. So what you want to keep in mind with Diels-Alder, what happens with the Diels-Alder reaction? What type of products do you usually get? Usually you get indo, and what about the stereochemistry? Do you conserve conserve the stereochemistry, right? You're not going to invert stereochemistry, okay? So you want to look for possibilities that would have that happen. So would 3 and 7 work? 3 and 7? What products are those? Indo or exo? Those are exo. 3 and 6? We already know that 3's exo. Is 6 exo? It's indo, but not 3 and 6 together wouldn't work. C, 6 and 8. So 6 is indo. How about 8? Will that work? Yes. So other things to look at with this besides indo and exo, you've got things completely attaching to different carbons. You've got here where you did not conserve your stereochemistry. So same with here, we've got the acid group moved carbons, different stereochemistry. So just be careful when you come across a problem like that you look at all your possibilities. Okay, down to the home stretch here. Okay, gel permeation chromatography is also called silica gel chromatography, more polar compounds elute first. Also called silica gel chromatography, less polar compounds elute first. Also called size exclusion chromatography, larger compounds elute first. Also called size exclusion chromatography, smaller compounds elute first. Also called GC, higher boiling compounds elute first. Also called GC, lower boiling compounds elute first. So GPC, or gel permeation chromatography, what is it looking at with GPC? Size, right? So it's going to be one of these middle guys. And what elutes first, larger compounds or smaller compounds? Larger compounds, so the answer is going to be C. Why was N-phenylmelamine used as the dienophile in our Diels-Alder reaction? Because it is locked in the S-cis conformation, is therefore more reactive, because it has electron donating groups and therefore is therefore more reactive, because it has electron withdrawing groups and is therefore more reactive, because it will add a UV chromophore to the product so we can follow the reaction by TLC, A and C, A and D, A, B and D, or C and D, okay? So when we're talking about S-cis, is that the diene or the dienophile? Diene, not the dienophile. Do we want electron donating groups or electron withdrawing groups for the dienophile? Withdrawing groups, so C. And then what about D? Did it add a chromophore? Yes, it did. So the answer is H, C, and D. Which of the following involves a carbocation intermediate? Diels-Alder, Friedel-Crafts, bromination of ethylbenzene, acid catalyzed dehydration of a secondary alcohol, base catalyzed saponification of an ester. Okay, Diels-Alder, is there an intermediate? No. Friedel-Crafts, is there a carbocation involved there? Yep. Oh yeah. Bromination of ethylbenzene, is there a carbocation involved there? No. Acid, so what type of reaction is that again? Radical. Acid catalyzed dehydration of secondary alcohol, is there a carbocation there? Yes. Base catalyzed saponification of an ester, is there a carbocation with a base? No. So we've got B and D, so the answer is G. Okay. So you will see a similar type looking exam on Monday. Make sure that you do arrive on time so that you have all the time that you need for the exam. It will be given between 12:30 and 2:30. So you want to make sure that you're on time to have all the time you can have. And if anyone needs to see me about academic success center forms, come